Okay, so this is the second part of the week 5 videos, and this one is going to talk about logistic regression. Hey, look, I'm using the from current slide. Yay, me! Logistic regression sort of, I think, fills kind of a unique role in that it is both a statistical model and a classification model. It's really like the one sort of model that I would consider both because the outcome of logistic regression is binary, meaning yes or no, 0, 1. Okay, so here's an example of linear regression. This is not logistic regression, this is linear regression. Linear regression, which you should have studied somewhere, typically in Stats 1. Here's a graph of income on the y-axis and years of education on the x-axis. And so this is some data, and you can see on the graph that there is quite a linear pattern to this. In other words, the more you go to school, the more money you make in general. So this, you could do a simple linear regression, and you could do a y equals mx plus b best fit line model, where you would get the slope and the intercept from the software, and you can do a model that you can then use to predict income based on education for novel cases. Okay, so that is the idea of statistical modeling. Again, for those of you that haven't had Stats 1, the simple linear regression model is really sort of like the first introduction to statistical modeling. It's always covered a little bit. Stats 1 doesn't get like super into it, but this idea of using data and then fitting a mathematical model, in this case a best fit line, and then you have the equation of that line and you can use it to predict things, and that's what I mean by model. I tend to just use the word model for like everything, but with this model, income is a continuous variable. It is not binary. Logistic is going to be binary. This would not really serve well for classification because the outcome is a continuous variable. That's not really what we want for classification, but this is a statistical model where you're predicting a quantitative variable. But it's the same general idea from linear regression that carries over into prediction models. So you can put the best fit line in. This is just Excel, and it's a little trend line fit. But when you have that line, you can now get the equation of the line, which is what this does, and you get a mathematically fitted best fit line. Excel does this with the regression feature in the data analytics toolkit or the limreg function. And you now have this income equals 6,050 times education minus 31,000. Typically, the intercept on these is not really like super meaningful in of itself. But the slope indicates that for each year of education, you go up by $60,000 or $6,050, which is a good deal. So keep that in mind when you go to school. But the idea here is that you can make a nice predictive model. This, though, is not something we want to use in classification directly. But the idea of statistical modeling with data is what we use in classification. The reason this becomes statistics and not classification is we're not going to want to predict a continuous outcome like this. Okay, so simple linear regression is not a classification algorithm. It doesn't work with labeled data, and the output y is a variable that's a continuous variable. So we don't want, this is not what we're going to use for classification. If this were like some kind of category, which it's not, then it would be classification, but it's not. This is something that is strictly quantitative and strictly part of statistics and not considered a classification model. So like, why am I showing you that? Because what about if I had data that looked like this? Okay, so this is height and whether or not somebody's over the age of 16 that I call an adult. So you can do yes, no, and binary. That's the same. Now, logistic regression, not linear, don't confuse the two. Logistic regression works with a binary outcome. That means the y variable is a 0 or 1. Okay, which now you can see how they carry over into classification, which is why I want to transition from simple linear regression, which is something that most people here will be familiar with, not all, into classification. And the logistic regression basically does that, because logistic regression literally sort of is kind of like linear regression, except now the y variable is not continuous, it's discrete, 0, 1. Okay, so if I do a plot of this data, you can see the difference between this and this, right? This is something you would use simple linear regression for because this is continuous. This, if you look at the data, you have here and here. So you have this categorical thing going on and not a linear pattern. Okay. Would you use linear regression for this? No. okay? NO. So you need another way to do a model to predict. What you want to do is you want to predict how high somebody is, how tall somebody is. I don't know why they call it tall and not height. Anyways, whatever. But you want to use a model that predicts whether or not somebody's an adult or not, and you don't have a continuous outcome that you're predicting. So what would you do with this? Okay, you would use logistic regression. Logistic regression is very similar to linear, but it allows for predicting a binary outcome, not a continuous outcome. Okay. But of course, we have to talk about a few other concepts before we can directly get into logistic regression. An odds ratio. An odds ratio is, I generally just consider it another way of expressing probability. Odds is the probability event over the probability of its complement. That's how odds is defined. So, for example, if the probability of winning is 1 in 3, that's probability because there's like 3 games being played and you win like one of them, so 1 in 3 is winning. The odds of winning can be expressed as the probability of winning, which is 1 in 3, over the complement, which is 2 in 3. So the odds become 1 to 2. So odds is really just another way of restating probability, and you can always get, if you have p, you always have 1 minus p because the complement is just 1 minus p. So it's the probability over its complement. Why am I bringing this up? Because the y variable in logistic regression is something called a logit metric, which is the natural log of the odds ratio. And this will range from negative infinity to positive infinity. And when the odds are 50-50, the probability here will be 50-50. So the y outcome for logistic regression is this odds ratio. Okay. So instead of having y equals a continuous variable, this is the outcome for logistic regression. Okay. And then this is the logistic regression model, which looks an awful lot like linear regression, except the y variable is replaced with this logit ratio, which what you can do with this is calculate backwards to find p. It's pretty easy, and I'll show you that. So it measures the probability of a binary response, which is the y variable, based on the mathematical equation with the x variable. Okay. And so this is a comparison of your linear regression where you just have this, which this is just y equals mx plus b. The beta 0, beta 1, in stats we use betas and not m and b. It's just notation. And same thing with logistic regression. And then this is the parallel. So these are kind of sort of the same thing, except the logistic regression, you're looking at a binary outcome, and then this one you're looking at a continuous outcome. Okay. This is just restating what I just said. In linear regression, the y variable is continuous and normally distributed. In logistic regression, the y variable is binary. Okay. So linear regression, your outcome is y, it's continuous. Logistic regression, your outcome is going to be binary, 0 or 1. That logit ratio, what it's going to do is it's going to give you a probability, which is going to be somewhere in here. And so your probability up here is going to be closer to adult and closer to child. You're going to get a probability out of that logit ratio. Okay. But the same idea of feeding the data in and creating a model, and these coefficients come from feeding the data in, which I did here for the logistic regression and got these. I think these are the exact numbers. I think I did this in Excel over the summer. And if you took stats 1, particularly with me, we went into Excel, we did these models, and we got slopes and intercepts. And you get these numbers from this data. This is the best fit line. And the same exact, these numbers are basically, it's the same idea of fitting in the beta coefficients to get the model. Okay. And so you can, of course, make a logistic model. Fitting the parameters, that's the business of going in the computer to get these, to get effectively the slope and the intercept. Okay. They're not quite a slope and intercept in logistic, but it's the same exact idea as with linear. Okay. Then, this right here, I didn't leave the algebra in, but in order, really what you want is you want to solve this for the probability, and the probability is like the probability of being an adult or child. And at a certain cutoff, they'll be an adult, and at a certain cutoff, they won't be. If you get a logit ratio of 0.5, then you're basically stuck. That would be like somebody who's like 14 years old and is like right on the edge of child and adult height. You know what I mean? Anyways, so taking this equation here, I don't know how many of you have had like, this would kind of be like pre-calculus, I think. What you do is you take these both to the power of e, because if you have ln x, you can do e to the ln x and you get x back. In this case, you get p back. So you can solve this for p, which is what I did here. So all this is down here is take this equation and solve it for the p, which once you have the betas and the x's, you can plug in an x and you can get a probability value, which is how logistic regression works. The computer will do this for you, but I did want to show you the algebra of this. Okay. And here, I did this. I went and took the data and put it into a model, and I got the coefficients. So this right here, instead of just being a theoretical model where it just has betas, which is the general model, I actually stuck all the numbers in and ran this and got the actual like model for this. So now instead of x, I have height. So I have the natural log of p over 1 minus p equals negative 38 plus 0.62 times height. And you're like, so what? Well, then what I do is I solve this for p. That's what this is, except now I have specific numbers. And this all, I mean, this is just a number. It's you know, you got to type everything into your calculator, but e is just the base of natural logs, 2.7. And as long as you have a height value, you can find the probability that a person is a child or an adult by plugging the height in. Okay. So I did that right here. So I took this. This is the data. And I calculated p. Okay. So this one, 0.3, this is the biggest one. So the tallest person has a predicted adult probability of 0.99. So for sure, somebody that's 72 inches is an adult. Likewise, 65 is 0.90, 68, 0.98. Now, somebody that's 60 inches actually has kind of an iffy, that's a person who would be 5 feet high. So this person actually is an adult, but they'd actually not be predicted as such. So this would actually, I think, be a misclassification. But if you're 47 inches, the probability you're an adult is extremely small. So this is the data, the first two, and then this is the model predictions. Now this is not, I didn't do a train test split on this. I just literally ran the model on the actual data again. So this are the numbers. Now what this is doing is, if p is less than 0.5, then we're going to classify them as a child, otherwise an adult. So I just simplified the predicted probabilities and made them binary. So if these are less than 0.5, they became 0, and if they're greater than 0.5, they became 1. And you can see this is the data. This one's incorrect. But I think all of the rest of them are correct. So except for the first row, the model gives us the correct prediction. Okay. So this is actually a really great example. I'm kind of congratulating myself on how good my own examples are of how a classification works, that we can actually see, like we can actually see algebraically all the numbers here, just like a high school math class, and you can actually sit and run through all this. Bigger and better classification models, though, work exactly like this. That's why I like to introduce the logistic model as something that you can see and feel and grasp the idea of a classification model. So a simple logistic model, this logistic model here that I just took these and got this model from this data. Then algebraically we solve this for p. And then we just put these numbers in. We put the height in, right? Because the height just goes in here algebraically, and you're just literally calculating p. I did this in a spreadsheet, and I just did this in Excel and just calculated these p's. But then what we do is if it's less than 0.5, we make it 0, and if it's greater than 0.5, we make it 1. But the model does work for, I think there's 10 cases. For 9 out of 10 cases, it works. There is one misclassification, but oh well. You will not get a perfect model unless you have like absolutely perfect data, which doesn't exist in reality. So logistic regression is considered a classification model. It is also a statistical model because it does use underlying probability distributions, whereas there are classification models that are not really statistics. I mean, I have a master's in stats, and there's some things in data mining that I would consider statistics, and other things that I would not. You do not really, when you're doing data analytics, you're not really a statistician. I mean, if you want to be a statistician, you still need to go and do all the math and stuff like that. But a lot of stuff in data analytics does not like use formal statistics. Logistic regression does. So it is an example of something that you would learn in an upper level stats class as well as do in data mining. But it's fairly simple, and it really does like show you how the classification is working. And with the more fancy models, it's difficult to do something like totally like concrete like this. Okay. So logistic regression is considered a classification model because it does predict categories, which even though you get probabilities as an outcome, you can use those and split 50-50, and then you can predict for the binary. And then these are, the red is categories. These would be considered not categories, but this is categories. Okay. And so how accurate was my model? Okay. So the actual class, there were 5 that were 0 and 5 that were 1. This is the actual data, and then these are the predicted. Okay. So I got 5 out of 5 class zeros right. The one that was wrong, so notice these are the zeros. 1, 2, 3, 4, 5. The one of the ones that the actual class was an adult was inaccurate, and that shows here. So this is the matrix of the confusion matrix of the actual versus the model. And in this case, we have a misclassification rate of 1 in 10, or 10%, which isn't too bad. So yeah, that's what we're going to look at. We're going to look at a lot of these classification errors stuff. Okay. So now this is expanding on things. Because really what we don't want to do is we don't want to just like run a model on the data that we already have. That's really not doing much. Except that when we run the data on the model, when we run the model on the data that we already have, we can use it to look at the accuracy. Now I did not split this. Because I only had 10 data values, but in a bigger data set you would actually split, and then when you looked at the accuracy, you would do that on the test data, not on like the original data like this. We'll see that. But this was like a teaching example, and it's only 10 values, so I didn't do that. But this right here is now, let's throw some new heights in. Let's say that we didn't know whether these people were adults or children, and all we knew is their height. So now what we can do is we can take these values of just height, right? Because we don't know whether they're adults or not. We don't have that. So we can take these and put them in here because we have this model and all the numbers out, and we just stick in the height values and we calculate P. Okay. And now that's a prediction. And so we get these P's, which are predicted values. These are not like P values from hypothesis testing. These are probabilities of being in a certain category. So this one is very, very low. So we're going to say that's a kid. Child, because it's way less than 0.05. This one's 0.3, so it's a child. This one's 65, so we're going to say that they're most likely adult. So we have new people that we don't know the true status of the new people. So this is not something, we're not testing anything here because we don't know the true status. But we can use this for predicting new values, which is the whole kind of cool goal. Because your goal in a classification model is to develop a model that you can then use to predict new things, right? So, you have a bunch of data on people that defaulted on their loans and their characteristics, and you use that to create a model, and then you take the future people who you have no idea whether they're going to default on their loans because they're just applying for a loan, so you don't have any default data. And you can use, though, the model that you created on the people that did default to create a model to predict the people that you're trying to determine if they might default. So that's the whole kind of point here to classification. It's good stuff. Again, be careful though. We'll talk more about biases and stuff too. So how would you actually graph this thing? So this right here, this is just the solve model. So how would you actually graph this? This is the y and this is the x. These logistic models always look like this. You don't really need to, like for this class, this is more of a stats thing, but this is a logistic regression curve, and they always look like this. So you have like, these are the zeros, and then you go up. You can see that this is the 50-50 mark, so there's kind of like a line here. So like this one here, that's our misclassification, by the way. So, yeah. Okay. You can also do multiple predictors. Now, different courses cover different things. Multiple regression is covered in statistics too, and we'll cover a little bit in applied data analytics. I'm not going to do multiple input for logistic regression, but very importantly, the example we just did, we're only using one x value, height. But when we do other models, which we're not going to do in this level of algebraic depth, but when we do other classification models, you can put multiple things in. So you could put height and weight and all kinds of other things. So the idea of making models with multiple input values is incredibly important. We're not going to do this like, we're not going to actually like hand calculate these like this, but we are going to do models where we have multiple inputs and we can look at that. Generally speaking, you don't want things to get like too out of control. I mean, how many additional input variables to put in? You don't want to throw like 50 variables in a model. Although I actually have done, in my prior life as a professional statistician, I've done models with like 50 input variables. That was an exception because it was like, that was my health insurance, like patient cost prediction thing. It was very, very complicated and took like a year to make. But in like a simple classification model for like mortgage stuff, you want to have maybe like 3 predictors, like income, like debt ratio, and like the cost of the house or something. You don't want to have like 10 million predictors. That gets kind of out of control. But you can put in as many as you want technically. But again, you know, you want your models to be like sensible and manageable. At a certain point, they get kind of whacked. Although, I mean, if you get into like higher level machine learning, artificial intelligence, I mean, obviously those are using way more complicated models. But for like a practical hands-on application of classification, you want to keep it like digestible. Okay. Binary outcomes of logistic regression at first, you're like, well, that has to be a 0-1 model. True. But it's very easy to create a 0-1 outcome because pretty much anything that you have a category of, you can create a 0-1 model by just sort of binning things. So whatever categorical data you have, if you have like cat, dog, bird, fish, you can translate that into dog versus not dog. So in other words, you can take something that's categorical and has sort of like multiple outcomes and very easily make it binary, which is why in stats, there's also something called the binomial distribution. That's totally separate from this. But logistic regression and things that use binary outcomes, it's actually easy to create a binary outcome because you just take whatever you're looking at and you say this or not this. So logistic regression becomes a lot more versatile than you would initially think. Of course, there's a traditional yes-no binary outcome, but it's very easy to create a derived variable with a binary outcome. As mentioned in the lecture when I talked about making derived outcomes. So that's actually a fairly easy thing to do. Okay, and this is the end of week 5. All right, thanks.